Hey everyone, today our tutorial is about launching and characterizing Tektite-A. Note that in the future when you want to launch Tektite-A, we will have a checklist in our blog post about this and it will be linked at the end of the video. Today we're going to do a characterization flight for Tektite-A. So the first thing you're going to do is select your rocket. I already made a couple of rockets, but if you haven't made one, just enter the name of your rocket. For example, you can enter qual rocket. Or you could put in like the date you make creating the rocket if you have multiple backup rockets. But I'm going to be using the version number of the flight computer. So we're going to do a characterization flight. What that means is that we need to set up the simulation. Now, since we're doing characterization flight, what that basically means is we need to know two numbers. This base coefficient of drag and this canard coefficient of drag. When you're doing the launch, you do not need to worry about any of these things. You can ignore them for now. Just go under the control system section, set the control method to fixed fin angle, and set the fin angle to 90 degrees. Finally, set this control time to twice that of your burn time. Since I'm using a 0.92 second burn, I'm going to use 2 seconds for my active control start time. Then, once you connect to the flight computer, which I don't have on me right now, you can just calculate the configuration and save it. Now, let's do the launch.
Just fold your parachutes.
Next, mass the rocket. Enter the target mass into the simulator. Enter in your control parameters. Connect to your rocket, calculate the parameters, and save the configuration. Next, turn on the flight computer. You can also turn on your altimeter at this point. Put on the payload tube. And fasten the rivets. Before putting your rocket on the launch rod, you must flip it over to arm it. Make sure to tilt the fin so you can see when it's armed. So now, flip it over until you see it move. And you can see that they're both vertical, which means that the rocket is armed. You can also see that by the red light inside of the flight computer bay. Okay, so we've returned from a launch. Take out your rivets. Now you can turn off your altimeter. And then you can put it on here too, so you don't lose the pin. And then you can turn off your flight computer. Now we're gonna read the data. So plug it into USB-C. You should see the yellow light, which means it has data. So connect to the rocket. Go into rocket configuration. Enter the name of your flight. For example, I'm gonna enter 720 second flight and hit download flight data. Now you'll see it load the flight data. All right, we're back from the launch. Let's look at the flight data. Now you probably don't have this much flight data, but select your launch, whatever you named it. I usually like to put the date of the launch and then the name of the launch. So for example, this is my active control flight. And this is probably not what your data looks like. Your data probably looks like it ends over here. But you can, right now it might be a little intimidating, but you can ignore all of this. First of all, you'll see everything like this. So what you can do is you can hide the simulation data since we don't care about that for now. Then you can hide the environment and control system data since we also don't care about that. Finally, you can click at the apogee, which is where the blue curve, the altitude is the highest, and drag to select only the ascent phase of the flight. Now, you can see that you can ignore the horizontal velocity since that's only useful if you're trying to analyze if your rocket has not flown straight. So you can just click on the variable to hide it. Now you'll see some interesting things. First, pay attention to the acceleration. You can see in this portion right here, we have the motor burn. This is creating a positive acceleration, which is pushing the rocket up. For the rest of the flight, we can see that our acceleration is negative, which means they're decelerating. This is the coast phase. Now you can see that when at 2 seconds, when we had our canards start tilting, you can see there's an increased amount of deceleration. This is a force of drag because our drag increased when we tilted the canards. Finally, you can see in our velocity curve, it goes up during the motor burn. And we see that we hit our peak velocity during motor burnout, and then after that it goes down. So now let's tune our two numbers. Our mass. So now what we're tuning is our base coefficient of drag and our canard coefficient of drag. First of all, you need to get all these numbers from your launch. So for these numbers, these three numbers, I like to pull them off of Weather Underground, but pretty much any app will tell you these numbers. Now, we had a fixed fin angle with a 90-degree fin angle and 2-second active control start time. Now, this is not the motor that I used in the launch, but it's fine because I'll show you a trick that the simulation has. Make sure to pull the mass that you measured at the launch, the propellant mass which you can pull from the manufacturer's website. And finally, in Open Rocket, you can graph reference area in the plotting option to see this. You can also graph coefficient of drag to get the base coefficient of drag rough number. Now that we have all of these set up, we can press Show Simulation Data. You can see that these don't really overlap, and this is because I have different motors selected. So what I can do is I can set the simulation start time to 2 seconds, or 1.3 seconds, which is the end of my motor burn. You can see that now my simulation sort of lines up. One thing is that you can see that this yellow curve right here, you can see there's a greater amount of deceleration in my simulation than in real life. So what we want is we want this yellow curve, the two yellow curves to match up. Right now you can see that over here, like in this part right here, that they do not match up. So you can see that they do match up pretty well during the motor burnout, after motor burnout, but before the fins tilt, which means that our base drag is pretty accurate. And I found generally Open Rocket's base drag is pretty accurate. I found a base drag of 0.52, and that's pretty much spot on. For our canard coefficient of drag, we can see that in the simulation, you can see that our simulated vertical acceleration is -57, while our vertical acceleration is -34. This means that our canard coefficient of drag is too high because in the simulation it's decelerating way more than in reality. So I'll try making it lower. You can see that's closer now. Looks like it's still a little too big. So I select 1.8. You can see they both pretty much perfectly line up. So now we know our base coefficient of drag is this from the Open Rocket, and that our canard coefficient of drag is 1.8. You're ready to move on to the simulation portion.